All right, let's look a little bit more into the electric field that is causing these currents to flow in a conducting material. Last time we talked about that current flows because there is a charge density that exists, or a current density, which we defined as J. We related that to the current as the integral of this current density through some cross-sectional area. Gives us the amount of charge moving through as a function of time. And we qualitatively argue that this J, this current density, must arise because of some electric field that exists. And it'd be nice to know what is the relationship between the current density and this existing electric field that is driving current. Now, this is something that is a more complicated question that we can't give a general answer to, but we can at least estimate it for a conducting metal. And in doing so, we'll see that there's a relationship between J and E that a lot of different metals and materials obey, at least in typical everyday limits. So let's consider some sort of conducting, let's say it's a piece of copper, where there is some electric field that is trying to, actually I'm going to draw in the opposite direction. There's some electric field that is trying to make the charge carriers, which in this case are little electrons, so these little red dots are going to represent electrons. And those electrons are then going to feel a force that is pushing them to the right, since the electric field points in the direction a positive charge would move in. Now, in this copper piece of material, there are the copper nuclei, which we are going to assume are in a fixed lattice. So these are going to be the positive nuclei, all fixed in a lattice. So we're going to assume that it's only the electrons that are free to move. Now, what I've drawn right here is clearly not to scale. Obviously, I'm drawing things way too big, and particularly I'm drawing the spacings and the sizes of everything within this piece of metal at clearly the wrong size. So we're going to make a couple assumptions that we will then justify. We're going to say the electrons are the only things moving. Or the only things that are free to move. The separation between the fixed nuclei and the electrons is quite large. All this is really saying is that the electrons don't collide with anything except themselves. So really what we're doing is we're treating this like a collisional fluid of electrons. And so all these electrons have various random motions, which we said last time. Actually, those velocities can be quite large, 10 to the 6 meters per second. In the presence of this overall electric field, though, the electrons, we believe, will start to drift very slightly towards the right. And it is that drift that establishes a current in the conductor. Now, everything I said above, and we should be able to justify in some way. I can't just make these approximations just because, willy-nilly. I should be able to have some sort of physical motivation or justification for this. And these are decent approximations, typically because the size of the electron is much, much smaller than, say, the mean free path. I think of this as the average distance between collisions. So all that is saying is that there's a lot of empty space in between the electrons as they're flying around. This is generally a very good approximation in this case. In this case, you could think, you're getting into quantum world, so what a physical size of an electron really means, you might debate, but there we're talking kind of classically like 10 to the minus 15 meters versus the mean free paths of these things, which is going to be more like 40 nanometers, so 10 to the minus 8 or so. So lots and lots of empty space in between the individual objects. An example of where this would be violated. What's an example? Like a pit of balls in like a playpen. Like a Chuck E. Cheese or something. Like all those balls, in order for the ball to get from one side of the bin to the next, it has to essentially rub up against a ton of other balls as it's moving. There's not a lot of space in between the individual balls in a ball pit, for example. So that is where, that would be an example where this approximation is not true. The distances in between individual objects is not much, much larger than kind of the size of the objects themselves. And the second approximation that can that helps justify this is that these mean free paths is smaller than the spacing between the copper atoms, or I'll say the metal atoms. So again, the mean free path we said was on the order of tens of nanometers versus spacing of nuclei in a copper lattice or a metal lattice, which is usually more on the order of micrometers. So again, so in this case, about 3 orders of magnitude, 2 orders of magnitude different. And again, why this is useful is this, again, allows us to say that all the collisions, everything that's really going on and causing the electrons to move is collisions with each other. And then, so we can really treat it like a collisional fluid. And then on top of that, we're putting this electric field, and we want to measure or understand how that drift atop of all those random motions is a result of the overall electric field. All right, just to give you a sense of the order of magnitude, I've already given you the two numbers. Now this is saying collisions are very frequent. Again, I can estimate the time scale of collision as the average distance the electrons travel divided by the velocity that they are traveling at. We said in the last lecture that, well, we just said that this was on the order of 40 nanometers, and the velocities are on the order of 10 to the 6 meters per second. So the top is 4 times 10 to the minus 8 divided by 10 to the minus 6. 4 is essentially 1 in estimation land, so this is on order 10 to the minus 14 seconds. So again, a lot of these collisions are happening very frequently. The actual direction that any individual electron is moving is constantly changing. And the velocities that they take, it's not always 10 to the 6, but it's some thermal randomized distribution. If you think back to physics 1, we talked about how there's the Maxwell-Boltzmann distribution, where there was a distribution of velocities that you can use to understand, statistically, the velocities of all the say air molecules in a room, or in this case, the electrons, in a conductor. Now, the fact that the collisional frequency is so large, or that the time between collisions is so small, that is actually, it's a little subtle, but that is actually very important because that essentially is telling us that even with this electric field imposed on top of all of this random motion, the electric field is not dramatically changing the characteristics of the electrons as they're moving about. This drift velocity is just, in a sense, a very small perturbation on top of a more or less chaotic random motion of electrons. If that weren't the case, if putting an electric field completely changed how the electrons were moving, say the electric field was so strong that all the electrons essentially got in march step and all moved in the same exact direction and collisions became very small, that actually would be a kind of poor version of a model for a superconductor. Because then all the collisions, which is the way that energy can be dissipated, all of that would go to zero. In that case, then there would be no energy really lost through all these frequent random collisions. But we are not going to assume that is the case. We are going to assume that the electric field that we're imposing is not really changing things like what I've written down as tau, the time in between individual collisions. And that will be important momentarily. So now to order of magnitude, let's actually estimate the drift velocity Vd based on some of these microscopic properties in the electric field. So if I think of an individual electron, say, it's bouncing around and it's randomly changing direction. And every time it collides with another electron or with something else, its velocity is essentially completely reset. So it has a new velocity that it kind of randomly draws from, say, a distribution of velocities, a thermal Maxwell-Boltzmann distribution of velocities. And since that happens a lot, its velocity is constantly being reset. So at any individual moment, the electric field is not able to considerably ramp up the velocity of the electron. Really, the electric field doesn't have much time to do that much, but it does have enough time to impose a very slight nudge in the overall velocity of the electron. So we can estimate this drift velocity as the acceleration it feels from the electric field multiplied by the time it takes in between collisions. Because again, after it experiences a collision, its velocity is essentially reset, but in between, collision A and collision B, its velocity is slightly tweaked because of the electric field. And this is how we will estimate the drift velocity that all the electrons are experiencing. Now the drift velocity, or rather this acceleration, is just F equals ma, so the acceleration is just the force the electron is experiencing divided by the mass of the electron, all times the time it takes in between collisions. You know that the force an electron is experiencing because of an electric field, and just minus charge of the electron times the magnetic field strength, divided by the mass of the electron, and then multiply by this tau. So on average, each electron picks up a little Vd, or a little drift velocity, in between collisions. And then once it collides, it kind of resets and starts over. So again, don't think of this as the electric field is constantly ramping this drift velocity up to higher and higher and higher values. Every time there's a collision, it kind of resets. So on average, it kind of only obtains at max this kind of drift velocity equal to, 2 order of magnitude, what we've written down as symbols right here. I might even actually, it's not terribly important, but I'll highlight it anyway. What I think is more important is now we can connect it back to the current density. So we also know that the magnitude of the current density, in this case for electrons, is going to be minus the number of electrons or charge carriers in this case, the charge of the electron, and then the magnitude of the drift velocity. That was from last lecture. Now we can put this all together, and we can actually write down that J, in this case, goes as minus little e, capital E, let me actually not skip right to the end. So minus NE, little e, then VD we said was little e, big E, mass of the electron times tau in that case. So we got the number density of the charge carrier is E squared, the electric field, tau, divided by the mass of the electron or something like that. I feel like I gained a minus sign that I should not have gained. I don't think this minus sign should be here actually. So this should have an overall minus sign. It ultimately doesn't matter. We're just looking qualitatively, but obviously the electron should be moving in the opposite direction as the electric field. So let me rewrite it in a more meaningful way. So this is saying J, I'll restore it back to vector form, is minus NE squared tau divided by mass of the electron, and that is all multiplied by the electric field. We have connected the current density J to the electric field strength E. And that relationship is related by, in this case, the proportionality between J and E is called the conductivity. And typically it is written as a lowercase sigma. So again, what that's saying is that J is some value multiplied by E. So this I will highlight. In general. When sigma is a constant, which in this case I'm saying that sigma is not some function of, say, the electric field strength, or we'll see later, it's not a function of, say, the potential difference being applied. This is a statement which is usually called Ohm's law. Or said another way, if sigma is a constant for a particular device or conductor or whatnot, we say the material is ohmic. So again, I want to emphasize that this J being related to the electric field as I've written it, this is a general result that we can always write down. And the relationship between the two is known as the conductivity. But it is not always the case where the conductivity is a constant. It might be the case that the conductivity is a strong function of other parameters in the problem. Usually all conductors have some dependence on temperature, so that the conductivity changes when things get really hot or really cold. In which case, so a light bulb, for example, a light bulb is an example of something that is not ohmic. We could always say that J is proportional to E in this way, but the conductivity would also be a function of temperature in that case. So for the model, the simple model we had up above, so I'll highlight in blue this thing here. For the simple model we sketched out, we were able to sketch it out where this conductivity actually was a constant of the properties of the material and the assumptions that we made of the collisional model of the electrons. And again, many conducting metals tend to be ohmic over some range of electric field strengths. Copper wires, for example, tend to be ohmic devices. Pieces of paper tend to be ohmic devices. That actually would have been a lab you would have done, where you can measure whether or not a piece of paper is ohmic, a piece of conducting paper is ohmic. But then you could have also seen that a light bulb is not. As you change the potential difference or the electric field that's driving current through the light bulb, you would not get the simple proportionality. Now, just to give you an idea of some of these numbers that we're talking about, for copper, the conductivity tends to be something like 6.25 times 10 to the 7. So we would find that would be an example of something that is very highly conductive. Something that is more of an insulator like glass is something like 10 to the minus 10. And then something that's more in between, like say silicon, where you might use that in a semiconductor, is something like 4 times 10 to the minus 4. And I think your book actually has a table of some of these as well, if you're curious, just to kind of what orders of magnitude are used for these sorts of things. All right, let me zoom out and take a look at all of this. All righty, so again, what is this saying? This is giving us a relationship between the electric field that's being established and causing current to flow. We now see exactly how that takes place. In the case of this kind of nice ohmic conducting metal, if I double the electric field strength, I double the current density, which since then the current itself is just an integral of the current density, that would say double the current. I would imagine if you took physics in high school, you had not seen anything like that before. You might have seen something like V equals IR, and you might have heard that as a statement of Ohm's law. So let's try to derive where that is coming from. Also, it's a more, I think, useful relationship in general, because we ultimately will be applying potential differences in order to get current to run in a circuit. And so it'll be useful to see how the properties of certain conducting apparatuses like light bulbs or space heaters or whatnot, how they accept or resist current depending on a given potential difference in properties of the material. So there I started microscopic and was trying to zoom out more and more to the macroscopic. Let's now go the other way and kind of meet in the middle. So let's start macroscopic and get more and more microscopic. So suppose I have something like a battery or something that can supply a potential difference. And my observer, after attaching the battery to maybe it's a copper rod or a piece of graphite, measures the current that passes through that particular object, be it copper, be it glass, be it graphite. What the observer would notice is that there are very different currents that result. And the observer might ask themselves, why might that be? And we have a clue as to why that is going to be the case. We saw in our previous, if I go back, we saw in our previous little toy model that whether or not current can more readily flow depended on this thing called the conductivity, which itself depended on properties of the material itself and kind of how many free electrons it had. That would be the number density. What are the charge carriers, and how are they spaced within the conducting material? Oops. So again, it might not be too surprising to realize that the amount of current that can flow through a certain object will depend on how willing or unwilling that object is to let current flow through it. So now let's get to our next big definition. So let us define the resistance of an object that has some current I which results from some potential difference V. So like the picture on the left, it might be that the battery supplies some potential difference that drives some particular current I. We define the resistance R as the ratio of the two, so V divided by I in this case. The units of resistance are volts over amps, which, as if you didn't have enough new units, we call the ohm. And the symbol we usually give it is that guy right there. What is this? Omega? Yeah. So again, this is a general result. You have some object that has some potential difference across it. There's some current that's being measured through it. The ratio of the two tells you the resistance of the object. And you can see just by rearranging, the resulting current is the result of the potential difference across the object divided by the resistance of the object. If something has a large resistance, this is aptly named, it is saying that the object resists current from flowing through it. If R was very big, I would be very small for a given potential difference. Now resistance, much like capacitance, is a property of the object. Why glass has a higher, in this case, glass has is an insulator. You can think of this as a very high resistance compared to say copper. That is all a result of the properties of glass versus copper. And this directly relates to our previous discussion. So let me consider kind of a simple toy resistor. So this resistor, I'm going to assume, is made of some material that I'm going to color red. And on the end, it is connected to some potential difference. So we might say the potential here is V plus, the potential at the other end is V minus. The resistor has some length L. If current is flowing, there's an E field that's established within it. In the geometry of the object, there's some surface area A that the current is flowing through. So should have made this blue. So there's some kind of surface area A at some length L that gives it some volume, which is A times L. Within that volume, there's an electric field which allows current to flow across some potential difference. We want to see if we can argue our way to get how the resistance depends on the properties of the material, like say the conductivity. If the conductivity is a measure of how easily current can flow, then you imagine that might play a role here in measuring the resistance. A low conductivity likely will mean a high resistance. And how it might connect to, say, the simple geometry of the object where the current is flowing through. So again, we can make some simple estimates based on stuff we've already known or have already talked about. We could estimate the magnitude of the electric field within this resistor. You know that there's a relationship between the potential difference and the electric field that is established as a result. It's just dV dx in that case. So for the electric field, since again I'm just trying to do this kind of simple approximations, I will estimate that derivative as the potential difference divided by the length of the object. And that's actually fairly reasonable for these sorts of things. There's some delta V, or just using the notation of your book, just V, potential difference, over some length. That gives you an estimate of the strength of the electric field. If this resistor were, say, connected to a battery, like the image I drew up here, that potential difference might be then the same potential difference that is set up by the battery. However, but E relates to J, the current density inside this resistor. We just said that J is some value called the conductivity times the electric field. And similarly, the current, which is just J over the cross-sectional area, in this case is just J times this cross-sectional area A in this case. So now we have three relations. We have one for the electric field relating to the potential and the length. We have the current density J as it relates to the electric field. And then we also have how the current relates to J and the surface area. So we're going to put these all together and then combine it with the expression we have above, where the resistance is the ratio of the potential difference divided by the current. And we're going to get how the resistance, capital R, depends on other properties of the system. So let's say I might first say that J is the conductivity times the electric field, but the electric field we said was V over L. J itself is related to the current, so we could say that I divided by the surface area is the same thing as J, which we just said is sigma V over L. And then we can rearrange this to get that V divided by I is the same thing as 1 over sigma A divided by L. Since, and then above, we say that R is 1 over sigma A divided by L. One over sigma, when you're talking about resistance, appears so much that just to make things more fun, this is sometimes called rho, or the resistivity. So you have the conductivity and the resistivity. They are essentially saying the same exact thing, just one is the ratio of the other. So in that case, we can also write this as rho, the resistivity A divided by L. And that also deserves a highlight. So again, what is this saying? This is saying the resistance of the object, how willing it is it wants current to flow through it, um, or how much it despises the idea of current flowing through it in the case of high resistance, is a function of properties of the material itself. That's the resistivity or the conductivity, as well as the geometry of the system. So again, not the exact same formula as capacitance, but kind of very similar in flavor, where these are things that are measured properties of the object, the conductor, in this case the resistor, whatever. And so we say then, while R equals V over I is always true, a resistor obeys Ohm's law when R is a constant, which again is just an equivalent statement of saying that the conductivity or the resistivity is a constant, going back to our previous definition of Ohm's law. So again, this kind of V equals IR is true in general, but when R is a constant, or said another way, R is not a function of the potential difference across the resistor, we say the resistor is ohmic. So if you had seen Ohm's law before, chances are you had seen it as V equals IR, which is misleading. Because again, V equals IR is always true, but when R is a true constant, that is a statement of Ohm's law. Ohm's law is saying that V is proportional to I by some constant. Double I or double V, double I as a result. Cut I in half, that meant that you changed the potential difference by a half. Again, for things that are not ohmic, for a given V and I, you could always take the ratio and get the resistance at that particular potential difference. But you would notice that as you went to different potential values V, you would notice that relationship would not hold. Maybe I'll just make a graph. To really nail home this point. And let's see. So suppose this is the potential difference across, I have some object and I want to establish a potential difference which can have different directions. I could establish it from one terminal to the other terminal, or I could do it in the opposite direction, and then I measure the current that results from it. Something that is ohmic might look like this. And why is that the case? This looks like a straight line. We think a straight line is y equals mx. But in this case, y is the current. The horizontal axis is v. If you look at v equals IR and rearrange it, then that just means that this is 1 over r. So if it does have a constant slope, this relationship between I and v, the constant slope means that 1 over r is a constant, or equivalently, that r is a constant across, no matter what the potential difference is. This might be contrasted with, say, a semiconductor, which might look something like this. in this case, the slope clearly is not a constant. At any particular v, I could measure I could calculate the resistance at that particular combination, but that r would not be a constant if I went to different potential differences. Again, in the case of a semiconductor, the things that make semiconductors useful is that there are, if you go back up to our, where I said the conductivity of silicon is not huge like copper, but not ridiculously tiny like glass, is that there are very few free electrons that can roam around and actually form a current. But that actually can be quite useful in electronics because then you can really have control over what those electrons are, or whatever the charge carriers are doing by tweaking the potential difference very specifically to get exactly what you need. Where in the case of, say, a copper wire, again, for practical purposes, the copper wire can behave kind of ohmically. But if, say, you had a short circuit or something else where the copper wire would heat up and up and up, it actually would eventually get to a point where it would start to behave non-ohmically. All right, so, but this will play an important role in the lectures to come. Let me just end briefly to motivate, we are now going to launch into circuits. So the good news is that what's to come really only requires one or two kind of rules, and once you understand the kind of very few number of rules, you can solve essentially any circuit problem that I throw at you. So these last two lectures have been kind of physics heavy, with the hope that this is something you probably have not seen before if you've taken a physics class. It really gets down to the details of kind of what is going on with current in circuits. But now we're going to spend then 2 days trying to understand circuits themselves, so that when you have, say, light bulbs and space heaters and whatnot connected to batteries and power sources, how can you calculate exactly what the current is where, for example. And just to motivate what's coming, we can talk a little bit about power. So suppose you have some device, like a resistor, that's hooked up to a battery source. We talked before about how this blue line is an equipotential surface, and this green line is also an equipotential surface. So that the delta V across the battery then must be the same as the delta V across the resistor. So if this is, say, if there's a 9-volt battery, 9 volts, there's a change of potential of 9 volts as you go through the battery, and then there must also be a change of 9 volts as you go through the resistor. And just by simple conservation of energy arguments, and we've argued this a little bit already, but sometimes it can be trickier, I think, with potentials. I think potential is a little, while it's very, very analogous to potential energy, it can be a little bit more abstract to think about rather than just talking about potential energy. Again, and that's why I think it's sometimes useful when you think about current flowing. So in this case, we would draw the current, the conventional current would be in the clockwise direction. Where again, if we think of the potential, or we think of conventional current as a bunch of positive charges moving, even though that might not always be the case, it helps us get some intuition on kind of what is going on. Because with positive charges, potential really is incredibly analogous to potential energy, where nature has a tendency of wanting to go from high potential to low potential. And if you want to go from low potential to high potential, something has to do work in order to get you there. Thinking of the mechanical example, in order for me to throw an apple into the air to reach some higher height, I had to do work to give the apple, in that case, the velocity so that it could soar up into the air. And then gravity and so then when it got to the top, near the ceiling, it had a lot of gravitational potential energy, which it then could tap into, which it turned into kinetic energy as it fell back down to my hand. And by conservation principles, what it gained it was balanced going up and going down. And it's the same sort of thing with batteries and resistors and capacitors. It's really the same for anything in a circuit. A positive charge wants to go from high potential to low potential, but if I draw the current the way I've just drawn it, a positive charge will enter through the negative terminal and be raised up to a higher potential, which is actually the opposite of what a positive charge wants to do. And so the battery is serving as I think Professor Ray called it a pump, where it is pumping up the charge to have a higher potential, or in this case, a higher electric potential energy, for that charge to then march off and go do work. And then when it got to the resistor, it had something that it could dump that potential energy into, and then once it got back to the battery, it had gotten rid of all that potential energy, was back to where it started. The battery could pump it back up again, and then it repeats itself. We can think of this also in terms of, the way I just argued it was in terms of potential. With a positive charge, it's the same exact thing in terms of potential energy. And then just all the signs are reversed if you have negative charges. It's the same exact idea. The mechanical example I like to think about of a circuit, rather than thinking of it as a pump, I like to think of, say, the battery as an escalator. So when a charge gets onto the escalator has to do work to raise the charge up to some higher elevation. It's then at some higher elevation where it's able to walk around until it gets to, say, a resistor or a downward slope hill, in which case all that potential energy it has gets lost as it goes down the hill. Then it gets back to the battery. It's back to where it started at the original elevation. The battery can then act as a charge escalator and rise it back up again, if a mechanical analogy works for you there. Now, as the charges are gaining and dumping energy from the battery and into resistors, a question that is useful to know is how much power is actually being generated. A light bulb, when a light bulb is 60 watts, that's 60 joules per second. That's a power, that is energy. So rather than talking about potentials, let's talk about potential energies getting converted into power. Luckily, this is super easy, because you know that the change in electric potential energy for a charge is just the potential difference it experiences multiplied by the small amount of charge that goes through that potential difference, where charge can either gain energy this way or lose energy, depending on whether the potential difference V is positive or negative. But in this case, we have a relationship between Q, the current, and time, where if dq dt is I, then dq is just I dt. Then I can divide both sides by t, and I can get the derivative of energy as a function of time is equal to I times V. How energy changes with time, that is indeed just power. So this gives the general relationship that the power through a particular source is the current that's moving through the source times the potential difference it experiences. And this is, again, a general relationship. If a current is going through a battery and the battery has some potential difference, this is telling you how much power is being supplied. If a current is going through, say, a light bulb, and that light bulb there's some potential difference across the light bulb, this tells you how much power is being supplied to the light bulb. For resistors, we can take this a step further. du equals V dq again. But we have not only an expression for dq, but we also have an expression for V in the terms of a resistor. When it's a resistor, we know the voltage is just the current times the resistance. And then dq is, again, I dt. This is I squared R dt. We can divide by dt. And we again get the power is I squared times R. And And this, of course, requires that you are dealing with a resistor, kind of obviously, because there's a resistance in the formula. Sometimes you'll also see this written as V squared over R. I'll let you convince yourself that is the case. It's just another substitution of V equals IR into the expression. But again, remember that this is for resistors. So you can also see how the resistance changes not only the current, but it changes the power that can be tapped out of a particular resistor, like say a light bulb. If a light bulb has a given potential difference, a high resistance, which ultimately slows down current, means that there's less power that can be delivered to the light bulb, for example. And this all ultimately comes down to when we want to answer these sorts of questions, like how much energy is being delivered to a light bulb, what sorts of currents are flowing, we now have to go into analyzing actual circuits specifically, which will be the next 2 lectures, so leading into Kirchhoff's laws. So this completes chapter 26, and then the next 2 lectures will be all on chapter 27 in your textbook. All right, see you soon.